Ladies and gentlemen, welcome to the third part of the video lecture series on option valuation, in which we are going to discuss the Black-Scholes option pricing model. And towards the end of the session, we are going to talk a little bit about using options as a hedging tool. But before we can talk about the Black-Scholes option pricing model, we need to prepare ourselves by understanding a few things about the normal distribution. So here is a normal distribution, ladies and gentlemen. What you see is a bell-shaped curve, and there are some properties. If you have taken a course in statistics, you would perhaps remember some of those properties, but here is the time to review some of them. Number one, the peak of this curve, ladies and gentlemen, represents the mean value, and we have standard deviations on either side of the mean. Towards the right of the mean, we have positive standard deviations. Here are the positive standard deviations. And towards the left of the mean, we have negative standard deviations in this area. You will also notice that the curve is split in half from the center, which means that half of the area is towards the left of the mean and another half is towards the right of the mean. Of course, the total area in the curve is 100%. You will also perhaps remember from your statistics courses that 68% of our data lies within one standard deviation on either side of the mean. So this is one standard deviation to the left of the mean, this is one standard deviation to the right of the mean, and 68% of the data, of the total data, is in this particular area. 95% of the data is within two standard deviations, so this is -2 standard deviation mark, this is the +2 standard deviation mark from the mean, and this entire area includes 95% of our information. And almost the entire information, 99.7% of it, is within the 3 standard deviations on either side of the mean. Right. To get a feel of how we can use a normal distribution, because we are going to need it when we solve the Black-Scholes option pricing questions, to get a feel of what we need to do when we get there, let's take up a simple sample problem. Suppose the mean exam score for your class is 65 marks with a standard deviation of 10 marks, and you want to find out the probability of having students who have scored above 80 marks. So what I'm going to do is I'm going to shift to my writing toolkit, and I'm going to solve this question there for you, and on the way I'm going to explain the various mechanisms involved, which will also include calculating a quantity called the standard normal variate, and then when we find the standard normal variate, we will need to look up its n value from the cumulative normal distribution table. So all of this when I move to my writing toolkit. So in this problem, we are given that the mean exam score for your class is 65 marks with a standard deviation of 10 marks, and we want to find out the probability of having students who have scored above 80 marks. So what you're seeing here in the diagram is that I've already plotted the mean score, and we know that on either side of the mean are the standard deviations. So let's just plot one standard deviation to the right of the mean. So because the size of one standard deviation is equal to 10 marks, if you go one standard deviation to the right of the mean, this would be the 75 mark point. And likewise, if you go one standard deviation ahead again, at the 2 standard deviation mark, you will find the score of 85 marks. Our point of interest is 80 marks because we want to find out the probability of having students who have scored above 80 marks. So let's think of it in this way. 80 marks is how many standard deviations away from the mean. So one standard deviation this size is 10 marks away from the mean, so this is 10 marks away. And if you go up to 2 standard deviations, you reach the 85 mark point, and 80 marks would be somewhere in between here. So let me just change the color and indicate that to you. So 80 marks would be somewhere here. So this might be the 80 mark point, and this is, well, this whole distance is 1 standard deviation, and you go half of this distance also. So this is 1.5 standard deviations then, 1.5 standard deviations away from the mean. So what we have done essentially at this point is that we have computed a quantity through visual inspection, and the name of that quantity is the standard normal variate. So let's just write that here. What we have found here at this point is called the standard normal variate, and it is denoted by the letter Z. If you don't want to use the visual inspection method, you can also use a formula to compute the standard normal variate. The formula is given as x, any value x which might be of our interest. In this particular example, the value of x would be 80 marks because that is the value of interest for us. So x minus the mean value, which is given to us in this question as 65 marks. And then you divide this difference by the size of one standard deviation. So I'm dividing it by sigma. Sigma denotes the standard deviation. So if we fill in the numbers, what we will find is, since the value of interest is 80, so I'm writing here 80 minus the mean value, which is 65, and we divide this by the size of one standard deviation, which is 10. So what we get is 85 minus 65 is going to give us 15, divided by 10 is going to give us 1.5. This is the same result which we found here. So 80 marks is 1.5 standard deviations away from the mean, and that is the value of Z or Z for us, which is known as the standard normal variate. Now from this point onwards, what you need to do is to go to a table which is known as the cumulative normal distribution table, and it will be provided to you in the examination also. So let me just write the name of that table: cumulative normal distribution table. So when we go to the table, there will be a couple of columns that you will find. One column will have a heading which will be labeled as D, and the other column, the adjacent column, will have N of D. So what the textbook will tell you is the column name is D and N of D. It is the same thing as Z and N of Z. So it's just a different letter which the textbook might be using. So Z is the same thing as D in the textbook, and N of Z, when we look at it, we will talk about it in a moment, is the same thing as the N of D. What N of D tells us, or N of Z tells us, is the probability of students lying below Z. So N of Z, so whether I write D or D or Z, it doesn't really matter, but because we are using Z for now, so let's just talk in terms of Z and N of Z. So what the N of Z, well, which is the same thing as N of D, is telling us is the probability of lying below Z. So now in our case, because the Z value is equal to 1.5, when we look up from the table N of Z, it will tell us the probability. N of Z will tell us the probability of having a score below 80. Why having a score below 80? Because 1.5 standard deviations corresponds with 80 marks. So if you go to the table, you will find that N of 1.5 is equal to 0.9332, which tells us that there is a 93.32% chance that the students will score below 80. But since the question asked us to find out the probability of students scoring above 80, and we know the fact that the total area under the normal distribution is 100% or 1. Therefore, once we know the probability of something below 80, we automatically can infer the probability of being above 80. So the probability of students scoring above 80 is equal to 1 minus 0.9332, which is going to give you 6.68% or 0.0668, which is equal to 6.68%. Obviously, if there is a 93% chance that students will score below 80, then there is approximately 7% chance that they will score above 80. So that is how we can solve this type of a question, which deals with a normal distribution. So what you need to do is to find out the standard normal variate and then look up its n value from the table. That's it for now. All right, so now we are ready to look at the Black-Scholes option pricing model. So what I'm going to do is I'm going to again shift to my writing toolkit shortly, and I am going to try and build the formula for you by using the intrinsic value of a call option, because the Black-Scholes model, as you're seeing from the display, was originally developed to price the call options only. And it will be good to remember for you that this model is applicable to only the European call options. So let us shift to the writing toolkit and let's try and build this model gradually, and then we will return to the PowerPoint. Alright, so let's understand the Black-Scholes option pricing model by using a little bit of an intuition and then bringing in the notational framework as well gradually. So Black-Scholes model, as we said before, was originally developed to price the call options, and it is applicable to the European call options only. Please remember that. So let's begin by writing, first of all, the intrinsic value of a call option at maturity. You will remember from a previous video lecture that the intrinsic value of a call option is given by a maximum of. So we are writing here, let me just erase this and write, first of all, for the sake of correctness, that the intrinsic value IV of a call is equal to a maximum of two numbers, which is 0 or S minus E. So assuming a call option to be in the money, which is profitable to be exercised immediately, we are going to pick up the positive number, which is the S minus E. So let's just write here the value of a call, C for call, is equal to, let's begin with its intrinsic value, S minus E. Now look at the two items here. S is the current stock price and E is the exercise price. Out of these two items, which one do you think pertains to the future? Well, S is the current stock price, so well, this is the current point in time, but exercise price pertains to the future, because the European call option will be able to be exercised only at the time of maturity. Which means that if you want to find out the current value of the call, everything must be brought back to the present point in time. This item is already current, but this exercise price is going to be applicable at a future point in time when the call option matures and is ready to be exercised or not exercised, whatever the case may be. But this is a future item, so this needs to be discounted to bring it back to the present moment. And you also remember from a previous video session that in the world of options contracts, or generally speaking in the world of derivative instruments, we use continuous discounting. So let's discount this exercise price E by multiplying it with the mathematical constant E and raising this to the power of minus risk-free rate times the time, where time is always supposed to be in years. So this is one part of it. Now we also want to know the probability that this call option is going to end up being in the money. That is, at maturity, it will be profitable to exercise it. So the probability of that happening is given by n of d2. So we multiply this by a quantity called n of d2. So this item multiplied by n of d2, n of d2, n of d2 here, right. We are going to talk about what d2 is in a moment. Likewise, now, once we know that this n of d2 is the probability of the call option ending up in the money, that is being profitable to exercise, then we also want to know that if it is that the call option is going to end up being in the money, then at that point in time, what is going to be the likely stock price? What is going to be the likely stock price? And that is given to us by a quantity called n of d1. So we write that here. So we multiply the stock price with n of d1, and we multiply the present value of the exercise price, this one, with a quantity called n of d2. So let me just write it neatly here. The formula, the Black-Scholes formula for valuing a call option is equal to S times, where S is the stock price, S times n of d1 minus the present value of the exercise price times n of d2. So these are two quantities. Now what is this n of d1 and n of d2? Before we can find out the n of a quantity, we must first of all find out the quantity itself. So we must know what is this d1 and what is this d2. So let's figure that out. And there is no easy way to do it because we are just applying the formulas. The derivation of these formulas is not within the scope of this course. So there is no other way but for you to remember these formulas by heart. So d1 is going to be equal to the natural log of S over E, where S is the stock price and E is the exercise price, plus another bracket inside which we write the risk-free rate R, plus we write down the standard deviation of the return of the asset and square it up, so sigma square divided by 2, close the bracket and multiply this bracket with time, where time is in years, and then divide this whole thing by standard deviation of the stock returns multiplied with the square root of time. So now this might look a little intimidating to begin with, but this formula, well, has remained the same since it was discovered, and it will be the same tomorrow. So when you're using the formula again and again and practicing some questions, it will become second nature to you in no time. So let me just create this a gap between the two things so that you know that this is a formula and it should not be disturbed by anything else. Right, so this is the formula for D1, and once we know what is D1, we can always go ahead to the cumulative normal distribution table and find out the n value for D1, which will give us the probability of lying below D1. And the next item then, you remember, is n of D2. So for that we need to figure out what is D2. The computation of D2, fortunately, is simpler. What you need to do is to write down the value of D1, which you computed here at this point in time, and from this you subtract this quantity, this one which I'm circling. So D1 minus sigma, which is the standard deviation of returns of the stock, multiplied by the square root of time. And once you've figured out what is D2, you can then go up to the cumulative normal distribution table and find out what is the n value for D2. So then what you will have then, you will know the stock price, you will know the exercise price, you will know n of D1, you will know n of D2, you will know what is the risk-free rate, you will know what is the time, and all these things will allow you to find out the value of the call option, because remember, a call option is equal to, the value of a call option is equal to S times n of D1 minus the present value of the exercise price here multiplied by n of D2. So that is fairly simple then. All that is needed to be done is for you to remember the formula for the call option value and also the formulas for D1 and D2. All right, so after having seen the call option formula and also what is meant by D1 and what is meant by D2 and how to look up their n values from the cumulative normal distribution, we can reproduce our results in a neat fashion here. So here you're seeing the call option formula with the definitions of D1 and D2, where n of D1 and n of D2 are found using the cumulative standard normal distributions. Let us take up a sample problem and put this formula to use. So we are looking at a call option with 6 months to expiration, so that is our T, but remember T has to be in number of years, so 6 months means half a year. So that will mean when we need to substitute a value for T, we will substitute a 0.5. We also know that the exercise price of this call option is $35, so this is the value for our capital E. The current stock price is $45, so this is the value for our S. The risk-free rate is 4%, which we will substitute as 0.04 where it belongs. And then we have the information about the standard deviation of underlying assets returns. In this case, the underlying asset is a share of stock, and its returns have a standard deviation of 20%. And the question is, what is the value of this call option? So I'm going to again shift to my writing tool and I'm going to solve this for you. And when we are done with the value of the call option, we are going to use the put-call parity condition to also find out the value of a put option. Right, so give me a few moments to shift to the writing tool and I'll be back in a moment. Right, so what we are given in this formula, let's first of all write down the inputs. We are given with the current price of the stock, S, which is equal to 45. We also know the exercise price, which is equal to $35. We know that this is a, how long will it take to mature? This is a 6-month option, so time is half a year because 6 months is half a year, so time is 0.5 years. We also know that the risk-free rate is equal to 4%, so we will use it as 0.04. And we also know that the standard deviation of the stock returns, so write that as sigma, standard deviation of returns is equal to 20%, which we will write as 0.2 when we substitute the values in the formulas. So when we are finding out the value of a call option now, what we are going to do is to start by finding out the value of D1. So let's reproduce the formula for D1 here. D1 is equal to the natural log of S over E, and then what you need to do is you need to add to this the risk-free rate plus the sigma squared divided by 2, and this bracket multiplied by the time, and all of this divided by the standard deviation times the square root of time. So let's just plug in the numbers. Natural log of S over E. So S is 45, E is 35. So we write that. So when you're calculating it on your calculator, you can do 45 over 35 and then calculate the natural log of it. How to compute the natural log on a Texas Instruments BA2 Plus, I showed it to you in the previous video lecture. So natural log of 45 over 35, so compute 45 divided by 35, whatever value you find, compute the natural log of it. Plus, now let's complete the substitution. R is the risk-free rate, which is 0.04, plus the value of sigma, which is the standard deviation, is 0.2 because it was 20%. So let's write 0.2 squared divided by 2, and we need to multiply this bracket by the time in years, which is 0.5 years, and then we need to divide all of this by 0.2 times the square root of time. In the previous step, when I was writing the formula here, I should have actually written sigma, and I wrote the value of sigma here, so I'm correcting that now. Right, so this is the formulation. So you can calculate it on your scientific calculator or on your financial calculator, whichever way it works for you. So what I usually do is I would I would break it into pieces. I would compute this. I would do 45 divided by 35. Whatever value I get, I will compute the natural log of it, and then I would work out, I would say 0.04 plus 0.2 times 0.2 divided by 2. Whatever I get, I multiply all of that with 0.5, and then write the consolidated value here for this whole expression, and then add this value to it and divide by the result of this number. So when we do this, now the final result is going to be, and you can check it on your calculator, the final result is going to be approximately 1.99, and we can round it off, so I can say approximately 2. So once I know the value of D1, I can go and to the cumulative normal distribution table and find out the value for n of D1, which will be actually n of 2. So when I go to that table, what I'm going to find is that the value against 2 is equal to 0.99772. So which tells me that there is a 97.72% chance of this option ending up in the money. That is, it is going to be profitable to exercise it, and there is a 97% chance of that happening. Now that we have figured out D1 and n of D1, we can compute D2. Let's just write the formula for that. What is the formula for D2? Do you recall that? D2 is going to be equal to D1 minus this quantity here, this quantity. So I'm reproducing that here, 0.2 times the square root of 0.5. So, well, I was supposed to write the formula, and again I've written down the value. So let me just erase that and put in the formula, which is sigma times the square root of time. So when we substitute the numbers here, so D2 is equal to, D1 we have already calculated, it was 1.99. So 1.99 minus 0.2 was the value for standard deviation, and the square root of time, where time is 0.5 years. So if you compute that, you will get approximately 1.85, and I am going to round it off to approximately, let's say 1.86, so that it becomes easier for me to find a value, the n value in the table. So I'm going to again go to the cumulative normal distribution table, because I'm searching for an n value for D2. N of D2 is equal to n of 1.86, and now if I go and look up in the table, what I'm seeing, let me get hold of the table. What I'm seeing is that against 1.86, I get 0.9686. So this becomes the n value for D2. So now that we have all the inputs, we can find out the value of a call option fairly easily. So the value of a call option is given by the stock price multiplied by n of D1 minus the present value of the exercise price, which I'm writing as this, and this present value is multiplied by n of D2. So let's separate out these quantities so that there is no confusion. So we can now plug in the numbers. The stock price was given to us $45, and we multiply this with n of D1. What was n of D1? Let's scroll back up and see. N of D1 was equal to 0.9772. So let's just put in that value there, 0.9772. And from this we need to subtract. Exercise price is 35, so we will need to compute the present value by multiplying 35 with e raised to the power minus the value for r is 0.04, the value for time is 0.5, so we write that there, and then multiply this with n of d2, which we found here, 0.9686. 0.9686. So I'm not going into how to find out the value for a quantity that is raised to the power of e, because we covered that in a previous video, and you can look up for the steps there how to do that on the calculator. So I'm assuming that you know this by now. When you do this now, 45 times 0.9772 is going to give you 43.974, and this whole expression is going to give you 33.2297 approximately. These are approximate numbers depending on how many places your calculator is set to display after the decimal. The rounding off would change the answer slightly, but that's all right. So for me, it is giving me $10.74 as the price of the call option. Now that we have found out the call option value, we can also quickly, while we are at it, find out the value of the put option. Remember the put-call parity? Put-call parity condition, put-call parity. Do you recall what is put-call parity? Put-call parity was as follows, that on the left-hand side, we had the protective put given by S plus P. On the right-hand side, we have the alternative strategy, where we had a call option and we had the present value of the exercise price, which we can write as this. So we can substitute the numbers because we now know what is the value for C. We already know what is the value of the exercise price. We know what is the value of the stock price. We know what is R. We know what is T. There is only one unknown, which is the P, and we can calculate that very easily by substituting the numbers. So let's just reframe this put call parity to indicate to us the value of the put option. So put option is going to be equal to C plus the present value of the exercise price minus the stock price. So we can substitute the numbers there. Call value we computed just now, 10.74 plus 35 times e raised to the power of minus 0.04 times 0.5. And from this we will subtract the stock price, which was given to us as 45. So let's just bracket out these terms so that there is no confusion anywhere. And if you solve this now, which you should be able to on your calculator, you will get approximately 6 cents, 0.06. So that is the value of the put option in this particular case. Okay, so now that we are done with the computation of the call price and also the put price, here is a comment for you to consider. What it says is that a put option may be worth more if exercised than if sold, while a call option is worth more when it is kept alive rather than dead. Well, why is that so? What does it mean? Let's talk about the call option first. Ladies and gentlemen, calls are worth more if you keep postponing the moment of exercising it. In other words, if you keep them alive for as long as possible, it will be better for you. This is because if you exercise a call too early and realize later that stock price is actually falling, what will happen? You will regret the fact of buying that stock by exercising the call, because you have just bought a stock which continues to lose value. And because the stock is losing value and you have bought it using by using your call option, by exercising it, you are going to be stuck with a low value stock. So that is the reason why it's advisable to keep your call option alive as much as possible for as long as possible. Turning our attention to a put option, put options are worth more if exercised because let's suppose the stock price falls to something that is very low. Let's say 0. Then there is no point in waiting to exercise the put, because a put option basically is the right to sell. And if the stock price has gone down so low, maybe 0, then the stock price is not going to go any lower. In fact, it will start going up. And the more it goes up, the lesser will be the value of E minus S. Remember, that is the intrinsic value of a put option. So if the stock price starts going up, the E minus S quantity will keep getting smaller. So exercising the put is beneficial if the stock price has already gone low enough and you believe that it's not going to rise, and you believe that the stock price is going to rise after that particular point. Let's also look at the difference between the European and American options, in the sense that when we use the Black-Scholes model, that is strictly for European options, we know that. So the problem is that the Black-Scholes model does not capture the early exercise value that occurs with a put. Like we discussed just a moment ago, if the stock price falls to zero and the option has not yet matured, and if it's a European option, you cannot exercise it. But if it's an American option, you could exercise it even before maturity. So clearly, an American option has more value in that sense. Because it will allow you to exercise the option early if you so want. Because the European option is not going to allow for an early exercise, therefore the price that you will compute using the model is going to be too low relative to that of an American option that does allow for early exercise. At this point, ladies and gentlemen, I will again shift to my writing tool, and we will talk about hedging, how options contracts can be used as a hedging tool. We will take the same example that we took in the previous topic of a cereal manufacturer, where he wanted to sell cereal boxes, and therefore he wanted to lock in a selling price for the cereal boxes by using a forward or a futures contract. So let me go back to the writing tool and we will talk about it there. Let us conclude this session by talking about the use of options as a hedging tool. Well, you will recall from the previous topic that we considered a cereal manufacturer who wanted to lock in the selling price of cereal boxes, and the risk profile looked as what I've already drawn for you to see here, where what you observe is that if the selling price increases on this side, if the selling price goes on rising, it will contribute to an increasing revenue on this side. So for example, if the price is this much, the revenue is this much. And if the price per cereal box rises to this level, then the revenue will also increase with it. But the bad side of it is that if the price per cereal box falls to this level, then the revenue would fall to this level. And if the price goes on falling further, then the revenue would fall to this level. So you would be in a losing position in that sense if the price per cereal box falls. To hedge against this price risk, we used a forward, or we could also use a futures contract, where we locked in the selling price by taking a short position in the forward or a futures contract. So if we were to represent that through a diagram, it would end up looking like this. So let's just draw a diagram and superimpose the payoff of a short position of a futures contract on this. So this is the risk profile, and let me change color to indicate the payoff of a futures contract when we take a short position. So if you take a short position, the payoff would be like this. So this is the payoff of a short position in a forward contract. In the bracket, let me just write forward contract, or a futures contract for that matter. And this one, the blue line here, let me change color again. This is the original risk profile. So now what is happening is that if the price falls to, let us say, this level, you will lose on cereal boxes and the revenue would fall to this level. But this loss here would be made up from the fact that you already have a short position in the forward contract, and that will increase in value to this level. At this price level, the payoff from the short position on a forward contract is this, and therefore you gain this amount. So let's change color here again. So this would be the gain. So what we are seeing is that this loss here is being offset by this gain here, and you are fully protected against the price risk. The problem arose that when the prices started to rise, let's say the price rose from this point, from the origin to this level, and you gained in the market by, you could have gained by selling the box in the open market for this price, and your revenue would have gone up to this level, and this would have been your gain then. But you already have a commitment to honor a forward contract or a futures contract where you have already promised to deliver the cereal boxes at a pre-specified agreed upon price. So you will have to honor the contract, and which will mean that your losses on the short position would be this. So what's happening here? What's happening here is that whatever you're gaining in the blue box at this place, this gain here is being offset by this loss here. So this is a loss here on the futures contract or a forward contract, and this loss is offsetting this gain here, which is coming out of this box. So while the position that we take in the short position that we took in the forward or the futures contract offered us protection when the prices fell, we had to sacrifice the gain when the prices rose up. If we, on the other hand, use an options contract as a hedging tool, so let's examine that possibility. If we think about options contracts, what will happen? If we want to lock in a selling price, we will have to use a put option on cereal boxes, because a put option is a right to sell, and that can be used to lock in the selling price. So let's represent diagrammatically what is going to happen. Let's first of all look at the profit and loss diagram of a put option. You will recall from a previous session that if you have a put option, then, and this is the exercise price, then as long as the market price is above the exercise price, that is in this region, the payoff remains zero. And if the prices fall below the exercise price, the value of the put option starts to increase. So if you had already paid a premium to buy the put option, then your situation would look like this, that you will keep losing your premium as long as the market price is above the exercise price, because in that case you will not want to exercise the put option. Why you will not want to exercise the put option is because you are already fetching a better price in the open market. So why to exercise the option and sell your stuff for a lower price? So if the market price is greater than the exercise price, you will not exercise the option, but because you already paid the premium, you will keep on losing that amount here. Once the market prices fall below the exercise price, you start winning on your put options. So first of all, you recover the amount of premium that you paid, and then the value of the put option goes on rising, so you keep on winning. So this is the diagram for a put option profit and loss. So this thing is the payoff line, and this thing is the profit and loss line. You will remember that from a previous video lecture. Now, if we superimpose this profit and loss line on our cereal manufacturer's risk profile, let us see what will happen. So let me change color one more time, and let's come back to the risk profile. So if this is your risk profile, where this is your change in prices and this is your change in revenue, and you deploy a put option to safeguard yourself against the falling prices, what's going to happen? Let's superimpose the put option profit and loss line. So let us say this is how it looks like. Maybe, okay. I could have chosen a different color maybe, so maybe I can pick up red, and I can draw this red line here, and then I can go this way. So what is happening? So as long as the price is falling now, if the price falls to this level, then on your original position there is a loss in revenue here, and your revenue falls to this level. But this loss in revenue is recovered by the gain on the put option here. So you gain here because the value of the put option has gone up here. So this is your gain. So this loss in this area is recovered by the gain in this area on the put option. So you're protected against the downside. So this is the gain from put. Gain from the put. and this is the loss from the market. Now, if the prices increase, let us say the price rises to this level now, and you would rather wish that you would sell your cereal boxes out in the open market at higher prices. If you were able to do that, this would be your revenue. This would be your revenue. In the case of a forward or a futures contract, you would have had this kind of a line here. It would have gone down like this, because on a short position on a futures contract, you would have kept on losing money if the market prices were rising. But we know with options contracts, you cannot lose more than what you paid as a premium. So there is a floor here. So you cannot lose more than this amount. So this is the maximum that can be lost. So for example, if this is the gain, you can still enjoy this gain, and from this gain you can just adjust that gain for a little bit of the premium that you paid and keep the remainder with you. So an options contract in this case is allowing you to enjoy the upside also, net of the premium that you paid for it, whereas a forward or a futures contract would not be able to do so.